AP Physics 1 Workbook, Unit 3, Circular Motion and Gravitation. Activity K, Friction as the Centripetal Force. Please read the scenario along with me. A student is attempting to determine the coefficient of static friction mu sub s between a coin and a steel plate. The student attaches the center of the plate to a freely rotating axis. For each trial, the student sets the coin on different positions in the steel plate and measures the distance r from the center of the coin to the center of the axis of rotation. The student also has a stopwatch to measure the period of the plate's rotation. Recall, the period is the time it takes for one revolution. Part A. Explain how the student can use this setup to make measurements that would allow the coefficient of static friction to be calculated. Be sure to explain clearly what rotational period must be measured and how experimental error can be reduced. The student could gradually speed up the rotation of the plate until the coin slips. Then time 10 full revolutions and divide by 10. So if you time full 10 revolutions, you'll get the time for 10 revolutions. Divide by 10, you'll get the time for one revolution, which is the period. Repeat this several times to eliminate systematic error. Part B. Starting with Newton's laws and basic equations for circular motion, derive an equation that relates mu, r, t, and fundamental constants. First, the horizontal net force is the centripetal force, and it's equal to mass times acceleration. I'm writing A sub c because the horizontal net force is the centripetal force. Static friction provides the centripetal force. So I'm going to be replacing the net force for static friction. So static friction, and simultaneously I can substitute for A sub c is equal to mv squared over r. And we can simplify it even further to write friction as mu times normal force. But normal force is equal to the weight. So friction equals mv squared over r can be rewritten as mu mg equals mv squared over r. Multiply both sides by r to isolate v squared. So mu, we also notice the mass cancels. And mu gr equals v squared. The speed will change depending on the plate the coin is placed, depending on where on the plate the coin is placed, but the period remains the same regardless, because the period of revolution is the time it takes for the plate to rotate, regardless of where the coin is placed. The speed and the period are related through the equation t equals 2 pi r over t. Velocity equals 2 pi over t. And so what we're going to do is we're going to take 2 pi over t and we're going to substitute, square everything. So v equals 2 pi r over t, and we're going to square everything. We're going to square this side and we're going to square this side. And we get v squared equals 4 pi squared r squared over t squared. And we will substitute this for v squared. Okay, and so we get mu gr equals 4 pi squared r squared over t squared. divide both sides by r. Okay, what that basically means is one factor of r is going to cancel both sides. And now the equation looks like mu g equals 4 pi squared r over t squared. Last step, solve for t squared. So in other words, let's go ahead and use the switcheroo. And we have a relationship that tells us t squared is equal to 4 pi squared r over mu g. And what this tells us is t squared is proportional to r. The student collects the data in the table shown above. Plot the data of t squared versus r in the graph below. So we're going to plot t squared versus r. Okay, so that's going to be our graph, t squared versus r. Let's go ahead and graph this. So at almost 2, we are at 0.1. So we're going to go over to 0.1 and up to almost 2. Well, we can see this is going by 0.2s, 0.2, 0.4, 0.6, 0.8, 1. So we're trying to graph 1.96. Well, this would be 1.8 right here. Halfway is 1.9, so 1.96 is almost at 2. It's right below 2. Too small to really notice a difference. The second one's very easy to plot. We're over to 0.2, up 4. We're exactly right here. The next one, we're at pretty close to 5.3 and 0.3. So here's 5.2, 5.4, so 5.3 is right in the middle. Okay, then we're going to go to about 7.3 over 0.4, up 7.3. That would be about right here. Oops. And in the last one, we're going to go 8.4 over 0.5, up 8.4. That would be right there. Now we need to draw a best fit line and then find the slope of that best fit line. Okay. Now to find the slope of the best fit line, you have to find two convenient points that cross through the corner of the graph paper box. I'm liking that point right there. And just got to kind of go up and down the line and search for another. Well, that's a pretty good point right there. And so from I'm going to make a slope triangle that goes from one point to the other. My rise is 9 minus 3.6. So 9 minus 3.6 is about 5.4 seconds squared. That's my rise. My run is going to be equal to this number here, which is 0.5, minus this number here, which is 0.2. So my run is 0.3 meters. Okay, let's figure out our slope. So our slope is rise over run. So that's going to be 5.4 seconds squared over 0.3 meters, which would be about 18 seconds squared per meter. We're going to need that information. Okay, so now if we take the equation that we're working with, and we had the final equation was t squared, and we're plotting t squared equals, let me write this down below, or actually right over to the side, we have room here. Okay, so here was our equation. T squared equaled 4 pi squared over mu g times r. Now, if we divide both sides by r, we get t squared over r equals 4 pi squared over mu g. What this tells you is this was your rise, r was your run, and rise over run is your slope. So that means the slope that we got, which was 18, is going to be set equal to 4 pi squared over mu g. So slope is equal to 4 pi squared over mu g, and you're trying to solve for mu. So what I'm going to do is I'm going to do the switcheroo with just those two right there. And mu is going to be 4 pi times r over mu times your calculated slope. Not mu, sorry, g times your calculated slope. There we go. Okay, so mu is 4 times pi times, let me see, 4 times pi squared. I'm sorry, not times the radius. My mistake, let me fix that. 4 pi squared, 4 pi squared. There we go. 4 pi squared is the rise. There we go. Okay, all of that is over, let's see, g. So 9.8 times the slope of 18. So our calculated mu, so we have 4 times pi squared is about 39.478. 9.8 times 18 is about 176.4. So our calculated mu, 39.478. It's around 0.22. You might even get as high as about 0.28 or 0.30, but you're going to be in a ballpark. You're not going to get a mu of 0.60 or 0.70. It should be about 0.20 something if you're doing it right. AP Physics 1 Workbook, Unit 3, Circular Motion and Gravitation. Activity L, Inertia in Space. Read the scenario along with me, please. A donut-shaped space station is built far away from the gravitational fields of Earth and other massive bodies. For the comfort and safety of the astronauts, the space station is rotated to create an artificial internal gravity. The rotation speed is such that the apparent acceleration due to gravity at the outer surface is 9.8 meters per second squared. The space station rotates clockwise. On the image to the right, sketch and label the vectors that represent the astronaut's velocity and acceleration. Well, if you recall, velocity is tangent to the circular motion, while acceleration is centripetal, pointing to the center. Part B. On the dot at the right represents the astronaut standing in the space station. Draw a free body diagram showing and labeling forces exerted on the astronaut at the instant shown. Draw the relative lengths of all vectors and the magnitudes of the forces acting. Well, here's the problem. Normally, we would draw the weight straight down. But in this instance, the only reason why an artificial gravity is created is because the space station is spinning, which means if the space station is far away from Earth, there is no gravity, no pull of gravitational force acting on the person. However, there is a normal force directed upward in the direction of acceleration. So the net force is the normal force. Part C. The astronaut drops a ball. On the diagram below, sketch the velocity and acceleration for the ball as seen by an observer outside the space station in an inertial reference frame. These are not free body diagrams. Okay. Well, in the first diagram, we're looking at after the ball is released before it hits the floor. Well, if the person has a velocity directly to the left, that means the ball has the exact same velocity directly to the left. So in other words, the ball's velocity should match the person's velocity because they're in the same reference frame. After the ball hits the floor. Now, this one's a little bit different because after the ball hits the floor, you now have and there is no acceleration for the ball as it's thrown because it's simply moving in a straight line like this. But then the space station will then rotate a little bit further, and the ball is going to run into the ground. So basically, the ball does this. The ball goes straight. Okay, it might seem like the ball is dropped, but the ball is basically released, and it's going to go forward just like the astronaut is moving forward. Then what's going to happen is the space station, the floor of the space station is right here beneath the astronaut. I'll draw that in blue right here. Okay, that floor is then going to rotate to this point right here, and it's going to cause the ball to ricochet upward off the floor. So in the beginning here, there's no acceleration acting on the ball because there's no gravity on the ball. The ball is just simply in motion at a constant speed, and it's going to remain in motion. That's Newton's first law. Now, what happens at this point right here after it hits the floor? Well, the floor is now, the floor is basically now moved and rotated, which means now the velocity is going to be this way. And when it hits the floor, there's going to be a normal force. And if the acceleration is this way, that's because the normal force and the net force are now that way. Part D. From the point of view of the person watching outside the space station, what path does the ball look like? A person outside the space station sees the ball travel to the left until it impacts again with the floor. Because remember, it's the floor that rotates. The ball is just seen moving straight line to the left. From the point of view of the astronaut inside, what path does the ball look like? The astronaut inside the space station sees the ball appear to be pulled downward and to the right. AP Physics 1 Workbook, Unit 3, Circular Motion and Gravitation. Activity M, Gravitational Fields. Please read the scenario along with me. The mass of Mars is 1/10 times that of Earth. The diameter of Mars is half that of Earth. Part A, derive the equation for the gravitational G, that means the gravitational field, due to a planet. Okay, well, first we're going to start with this. And that is Fg on the surface of the Earth is equal to mg. Okay, now I'm going to call this m as like a person on the surface of the planet. Okay, and if I were to draw a picture here, here's a person on the planet, here's the planet, not drawn to scale, of course. The person will be m2, the planet will be m1. Well, the gravitational force is also, this is at the surface. The gravitational force is also big G m1 m2 over r squared. This is universal. Anywhere. Surface, anywhere, doesn't matter. So what that allows you to do is, if those are the same, those two are the same. And that's exactly what we're going to do. We're going to set m2g equal to big G m1 m2 over r squared. And you can see that m2 cancels on both sides. So we are left with big G is equal to, or little g is equal to big G m1 over r squared, where m1 represents the mass of the planet. So most times we're just going to write this as little g equals big G, big M, because a planet's mass is usually pretty big. So we'll just write it as big M over r squared. And that's usually the way we'll represent this equation. Part B. Let the gravitational field strength on the Earth's surface. Okay, that's what G is. So G is the gravitational field strength on the Earth's surface. Derive an expression for the gravitational field on the surface of Mars without plugging in values for the mass and the radius of Mars. Your answer should be a number multiplied by G. In other words, we're going to find an answer how many times greater or less than G, the acceleration due to gravity on Earth. Your answer for each line of the derivation, explain what was done mathematically. So the easiest way to do this is to talk about what's done first. So I would suggest you pause or rewind the video as you need to, write down each description, and then you can write mathematically what's going on in the left-hand side. Step 1. The acceleration due to gravity on Earth's surface is given by G on Earth is equal to big G, mass of Earth, divided by R of Earth squared. Step 2. Plug in the relative relationships for the mass and radius of Mars. Plug in a 1 for G. So gravity on Mars is now equal to 1 for G. And we were told that the mass of Mars is 1/10 the mass of Earth, and the diameter is half. So if the diameter is half, the radius is half. So we're going to plug in 1/10 for the mass divided by 1/2, and we're going to square that. Okay, so we get 1/10 I'll hold off on that part. The next part, we simplify the equation. So we have G on Mars is equal to, and we have 1/10 on top over 1/4. Simplifying the equation again, we have 1/10 times 4 over 1, right, is 4/10. And the acceleration due to gravity on Mars is approximately 4/10 or 2/5 the acceleration due to gravity on Earth. So we can write that as gravitation on Mars is equal to 4/10 the gravity on Earth, or you could write it as the gravity of Mars, the gravitational field on Mars is 2/5 the gravitational field on Earth. Either of those would be fine. Part C. A rock is dropped 2 meters from the surface of Mars. Does this rock take longer or shorter time to fall than a rock dropped 2 meters above the surface of the Earth? Justify your answer without using equations. The acceleration due to gravity on Mars is less than on Earth. Therefore, it will take longer to fall the same distance because there is less pull of gravity. Part C. On the internet, a student finds the following equation for time an object will fall to the ground from a height h, depending on the mass and the radius of the planet it is on. And they come up with t is equal to the square root of 2 times the height times the gravity constant g divided by the mass of the planet times the radius of the planet squared. Okay, and the square root of all that. Regardless of whether this equation is correct, does it agree with your qualitative reasoning in part C? Well, what did we say in part C? If g is less, right, time will be longer. So, yes, it does agree. Both mass and radius of Mars are smaller than mass and radius of Earth, which leads to a smaller acceleration and a larger time from a constant height. This equation shows that if both mass and radius are smaller, the time to fall will be larger, which is exactly what we predicted. Part E. Another student deriving an equation for time the time it takes for an object to fall from height h, makes a mistake and comes up with t equals the square root of r squared over 2g mh. Without deriving the correct equation, how can you tell this equation is not plausible? In other words, that it just does not make physical sense. Well, for one, let's look at the height. If you increase the height, that means you drop it from a higher height. If h is on the bottom here, that means t goes down. H goes up, t goes down. But that doesn't make sense, because if you drop something from a higher height, it takes longer time, not shorter time, to fall. So h shouldn't be in the bottom of the equation. Again, if you increase the height that the object is falling from, then the time should not decrease, which is what the equation says. Also, another thing, the units do not give you seconds if you analyze them. Okay, so to kind of break down what that equation would be in terms of units, here's how it does not make sense. The unit for r is meters, so it would be meters squared over 2, which has no unit, so I'm not going to worry about 2. G has the unit of newtons, meters squared per kilogram squared, times mass, which is kilograms, times height, which is meters again. So now newtons, mind you, a newton is a kilogram meters squared per second squared, or kilogram meter per second squared. Kilogram meter per second squared over kilogram squared times kilogram times meters. Okay, now things are, wow. You have kilograms times kilograms does cancel with kilograms squared. You have meters canceling with meters, but that's not the case. It shouldn't cancel with meters. You want meters times meters. Let me see. No, that does not cancel. I'm sorry. So meters times meters is meters squared, cancels with that meters squared. And so we're left basically with this. We're left with 1 over seconds squared, which is 1 over seconds when you take the square root. 1 over seconds is not the unit of time. So the units don't make physical sense either if you analyze them. AP Physics 1 Workbook, Unit 3, Circular Motion and Gravitation. Activity N, Newton's Law of Universal Gravitation. Please read the scenario along with me. A student is given the following orbital data for some of Jupiter's moons and is asked to determine the mass of Jupiter. Assume the orbits of these moons are circular. So we are given 1, 2, 3, 4 moons, and we're given the orbital radius and the orbital period of those orbits. Part A. Write an algebraic equation for the gravitational force between Jupiter and one of its moons. Well, the gravitational force equation would be F sub g equals big G m1 m2 over r squared. But we should be writing it a different way. So mj is the mass of Jupiter. So we're going to write g mj for mass of the moon divided by r squared. And that's our Newton's law of universal gravitation formula that would relate the gravity of Jupiter and one of its moons. Now, for part B, use your expression for part A and the assumption of circular orbits to derive an equation for the orbital period as a function of the orbital radius. We are basically deriving Johannes Kepler's third law of planetary orbits, okay, which will end up being the period squared is proportional to the cube of the radius, okay? Let's see how we get that. Start with the following. Write the gravitational force between Jupiter and one of its moons. Okay, well, we did that. We're just going to recopy it down. So F sub g is equal to big G mj mm over r squared. The gravitational force is a centripetal force responsible for keeping the moon in orbit. What does that look like? G mj mm over r squared is equal to mass of the moon v squared over r. Gravity is a centripetal force. Remember, ladies and gentlemen, to pause while you're writing each description, and then you can resume copying the equation derivation on the left-hand side. Next, cancel r and the mass of the moon. Mass of the moon cancels, one factor of r cancels. And we're left with G mj over r equals v squared. Now, we're going to substitute 4 pi squared r squared over t squared for v squared. Where did we get this? Well, recall that the speed, the orbital speed, is the circumference, 2 pi r, divided by the radius. So if you square both sides in this, you get 4 pi squared r squared over t squared. Okay, and we are going to substitute this for v squared in the equation right here. G mj over r equals 4 pi squared r squared all over t squared. Step 5, solve for the mass of Jupiter. So solving for the mass of Jupiter, we multiply by r, divide by g, and the mass of Jupiter is equal to 4 pi squared r cubed, because you multiply both sides by r, and now you have r times r squared. That's r cubed. All over g times t squared. And then in our last step 6, we're going to solve for the period squared. So what I'm going to do is I'm going to do a little switcheroo, and I'm going to switch t squared with mass of Jupiter. And I get t squared is equal to 4 pi squared r cubed all over g times the mass of Jupiter. Okay, and what we have is the period squared can be written as a function of the orbital radius cubed. Period squared relates to the cube of the radius. This is known as Kepler's third law. Part C. What quantities should be graphed to yield a straight line whose slope could be used to determine the mass of Jupiter? Well, start with the equation. Let's write it down. So t squared equals 4 pi squared over gm mass of Jupiter times r cubed. What I'm going to do is I'm going to divide both sides by r cubed, and we get t squared over r cubed equals 4 pi squared over g times the mass of Jupiter. And what this should show you is this should be our rise. This should be our run. And rise over run is slope, which means that is your slope. So what must be plotted to yield a straight line with a constant slope? T squared versus r cubed. We should be graphing period squared versus radius cubed. Now in part D, we're going to go back up to the top of the activity, and we're going to complete the data table by completing the two quantities that need to be graphed. Okay. So in other words, we're going to square the period and cube the radius. S squared would be t squared, meters cubed, well, that would be r cubed. So starting with t squared, if I take 2.08 times 10 to the 7 and I square it, I get 4.3 times 10 to the 14. If I take 2.49 times 10 to the 7 and I square it, I get 6.2 times 10 to the 14. If I take 4.05 times 10 to the 7, I get 1.64 times 10 to the I'm actually going to write this a different way. Instead of 1.64, I'm going to write it as 16.4 times 10 to the 14. You see, if I put that in my calculator as 4.05 times 10 to the 7, and I square that, I actually get 1 point, just so we can clarify this, 1.64 times 10 to the 15 power, okay? But that's written in proper scientific notation. So all I really did is I moved the decimal point over 1 like this, and that brings the exponent down from 15 to 14. Why would I want to do that? Because I want each of these to be times 10 to the 14. It'll make it much easier to plot, much easier to graph. So last one. I'm going to go 5.03 times 10 to the 7 and square it. And when I do, I get 2.53 times 10 to the 15. And just like I did last time, I'm going to move this over 1, which knocks this exponent down by 1. And it's 25.3 times 10 to the 14. So I've got all of them times 10 to the 14. And so what I'm going to be plotting, I'm just going to be plotting the prefix of those numbers right there. You'll see shortly. R cubed, similar idea. If I take 1.12 times 10 to the 10 and I raise it to the third power and cube it, I get 1.4 times 10 to the 30. If I take 1.26 times 10 to the 10 and I cube it, I get 2 times 10 to the 30. Notice the pattern. I want everything to be times 10 to the 30, right? So if I take 1.71 times 10 to the 10 and I cube it, I get 5 times 10 to the 30. And finally, if I have 2.02 times 10 to the 10 and I cube it, I get 8.24 times 10 to the 30. What I'm actually plotting, though, would be the prefix of those scientific notation numbers right there. Okay, let's go ahead and plot those. Remember, t squared is my y. R cubed is my x. So I'm going to start by going over 1.40 and up 4.3. .40 is here. 4.3, well, kind of like 4.5, so it'd be right here. The next one, I'm going to go over 2 and up 6.2. Here's 6. So I'm kind of going over not quite 6.5. Right there. My next one, I'm going to go over 5. And then I'm going to go up 16.4. So up 16.5. So over 5, up between 16 and 17. About right there. And the last one, I'm going to go over 8.2, 8.2.5, and up 25, almost 25.5. So here's 8.2. This is 8.4. 8.3 is in the middle, so 8.2.5 is closer to 8.2. And we're going to go all the way up to 25.3. Well, here's 22. That would be 21, 22, 23, 24, 25. So the last point, 8.24 and 25.3, well, 25.3 would be above 25, which is here. So we can go and make the last point about maybe right there, just a little above. And what we're going to do is we're going to make a nice best fit line through that data. So if you're doing this on paper, get a ruler and do it. If you're doing this electronically, then search up the line function and draw a line. Don't freehand draw it. Get an actual line in there. So it might look something like this. There we go. Okay, now what you're looking for, again, to be able to do this right, you're looking for 2 points where the line intersects the corner of the graph paper. I like that point right there. And I like that point right there. So what I'm going to do is I'm going to draw a slope triangle from one point to the other point. Find this on your best fit line as well. And what we have here is we have a rise that goes from 4 to 12, right? So we have a rise of, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Rise. Now the rise is not 8. These are where we got to be careful. The rise is not 8. It's 8 times 10 to the 14. Okay, you got to be careful. The run. And then we get the run by going this number here, which is 3.8, and this number here, which is 1.2. Subtract those. And we get a run of 2.6. Now, it's not 2.6 necessarily. it's 2.6 times 10 to the 30. So you have to make sure your rise and run have the appropriate suffix for the scientific notation, okay? Because that's really gonna make the slope much more accurate. Okay, so we got that part. Okay, now over to the side, let's try something here. We know that according to this, the slope should equal 4 pi squared over g times the mass of Jupiter, right? And well, we can swap those two, and the mass of Jupiter can be found by taking 4 pi squared over g times your slope. So let's figure out what your slope is. Okay, the slope is going to be about, in my case, let's see, 8 times 10 to the 14 over 2.6 times 10 to the 30. All right, so 8 times 10 to the 14 divided by 2.6 times 10 to the 30. And we get approximately 3.08 times 10 to the negative 16. So that's what the slope is, right? Okay, so the mass of Jupiter would be 4 pi squared, which, by the way, is 39.5 when you multiply 4 times pi squared, times g, which is 6.67 times 10 to the negative 11, times the slope, which we found to be 3.08 times 10 to the negative 16. So 4 times pi squared is 39.48. And we have 6.67 times 10 to the negative 11 times 3.08 times 10 to the negative 16. We have a really super small number here of 2.05 times 10 to the negative 26. Okay, and divide those two numbers and we'll have the approximate mass of Jupiter. So 39.48 divided by answer, we're looking at about 1.9 times 10 to the 27 kilograms. Keeping in mind that the mass of the sun is on the order of times 10 to the 30 kilograms, you can see the mass of Jupiter is not that much less. Okay, now even though the problem didn't ask us to continue this, I wanted to continue doing this with you because there are certain problems and actual AP exam questions that have asked this exact same thing. Okay, but now the question continues by saying part F, 2 identical probes are sent to study one of Jupiter's moons. Probe A is geosynchronous orbit around the moon, while probe B rests on the surface of the moon and rotates with the moon. Geosynchronous means this. Here's the moon, and as the moon rotates, this spins. This revolves. So what this tells you is that if I have a position here where the probe is right above that position on the moon, when the probe is rotated to this position here, it'll be right overhead. So every single point, the probe is going to be right directly overhead. That is called a geosynchronous orbit. That basically means that the satellite orbits along with the actual rotation of the moon. Okay, now the one on the surface of the moon is also rotating with the moon. The biggest difference, of course, would be the radius. So here's the moon. Okay, you have one probe, probe B. Probe B is on the surface. Probe A is away from the surface. Here is the radius that separates the probe from the center of of the moon would be r, and then this probe right here would be a much bigger r, right? Because it's at a farther radius away from the center of the moon. Okay, rank the magnitudes of the following gravitational forces from greatest to least. If two are the same, clearly say so. Okay, it's always best to do your justification before you do your ranking. So let's take a look at our analysis here. Newton's third law states that A should equal C, B should equal D, and E should equal F. Okay, let's read these carefully. A says the force of the moon on the probe, and then C is the force of probe A on the moon. Well, sure, those should be the same. Part B says the force of the moon on probe B, D says the force of probe B on the moon. Yes, those should also be the same. Again, Newton's third law tells us this. And then E and F, the force of the probe of A on B and the force of the probe of B on A. Definitely those should be the same as well. So Newton's third law tells us those should all be equal, okay, in terms of forces. The force of gravity depends on masses and the distance between the masses. The probe's masses are so tiny relative to the mass of the moon that the gravitational forces described in E and F are tiny compared to those in A, B, C, and D. Okay, so again, the mass of the moon is much more significant than the mass of either probe. So the masses that are involved in comparing the gravitational force in probes A and B, those are going to be much, much smaller than comparing the gravitational force between the moon and probe A or B. Since the force of gravity also depends on the distance between the objects, scenario B and D, B equals D is larger than A equals C. Let's see why. Again, let's focus on our picture here. Here's the moon. There's the center. There's probe B, a distance r away from probe B. Probe A is way out here at a larger orbit, much larger radius. Since F is proportional to mass times mass over r squared, probe A has a larger radius from the center of the moon, therefore a smaller gravitational force. So A and C, A equals C needs to be less than B equals D. Okay, so far we get the ranking B equals D is the greatest, which is greater than A equals C, which is greater than the probes equaling each other, which is E equals F. AP Physics 1 Workbook, Unit 3, Circular Motion and Gravitation. Activity O, the gravitational force. Please read the scenario along with me. Angela, Blake, and Carlos are studying the data table to the right, which shows the mass, orbital radius, and orbital period of 4 planets. They note that the orbital period increases, but disagree about why this happens. Their arguments are as follows. Angela says, it appears that the more mass a planet has, the longer its period is. This is because more massive planets are more difficult to move, so these objects are slower in their orbits. Blake says, no, all planets move at the same speed around the sun, but planets with greater orbital radius must make longer circumference orbits, causing their orbital periods to be greater. Carlos says, it is the case that farther radius planets must make farther circumference orbits, but the farther planets also go slower because there is less gravitational force acting on them. For this problem, consider one planet of mass m making a circular orbit around radius r around the sun of mass big M. Let v be the speed of the planet as it orbits the sun, and t be the orbital period. Part A. Beginning with the basic equations for gravitational and centripetal force and an equation that relates speed and period of circular motion, derive an expression for the orbital period of this planet in terms of r, m, big M, the mass of the sun, and v, and any physical constants necessary. Note that it may be helpful for Part B for you to number your steps so that they are clearly referred to later. I would also suggest you write down the description of each step, pause the video, and then write down mathematically the equation derivation on the left-hand side. Let's begin. Step 1. Let's start by writing the force of gravity between the planet and the sun. Gravitational force would be big G, mass of the planet, mass of the sun, divided by r squared. Step 2. The gravitational force is the centripetal force holding the planet in orbit. G times the mass of the planet times the mass of the sun over r squared is equal to the centripetal force, which is the mass of the planet times v squared. Make sure you understand that that's a subscript, times v squared over r. Step 3. Divide both sides by the mass of the planet and multiply both sides by r. In other words, r and m cancel. Mass of the planet cancels, one factor of r cancels. And we have in step 3, g times the mass of the sun over r, the orbital radius of the planet, equals v squared. Step 4. Substitute 2 pi r over t in for the speed. This means we sub 4 pi squared r squared over t squared for speed squared. So be prepared to sub this for this. We had just done this in the previous activity as well. G times the mass of the sun over the orbital radius is equal to 4 pi squared r squared over t squared. Step 5, multiply both sides by r. Cancels on the left, forms r cubed on the right. Okay, and so far, we're also in step 5 going to swap and solve for t squared. Okay, so not only do we have GMS over, GMS equals 4 pi squared r cubed over t squared. And so we do need to remember to swap those out, and we get t squared is equal to 4 pi squared r cubed over g times the mass of the sun. Okay, and we can leave it like that. You can leave it like that, or you can square root both sides to get the actual period, but I think this is fine. The period squared relates to the cube of the orbital radius. Part B. Your work in Part A can be used to support or refute the arguments of the 3 students. For each student, explain which aspects of the reasoning, if any, are correct, if any are incorrect, and cite steps from the work in Part A, not your final answer, that explain and support or refute each aspect. Well, let's review what they said. Angela says that more mass, longer period. Well, if you notice in step 2, mass canceled. Mass of the planet canceled. Mass doesn't have an effect on the orbital period at all. So I think we can safely say that Angela is incorrect. Angela is wrong. The mass of the planet has no effect on orbital period. The mass of the planet cancels out. Blake says the orbits move at the same speed around the sun, but the planets with greater orbital radius must make longer orbital circumference orbits, causing their orbital periods to be greater. Blake is also incorrect. If we look at step 3, step 3 shows that the speed of the planet is related to the orbital radius. The farther you are, the slower the speed. Okay, so step 3 shows that the speed of a planet, the sun depends on the speed that the planet orbits the sun depends on how far it is from the sun. He is correct in thinking that V 2 pi r, the bigger the r, the larger the t. That part's true. But his assumption is incorrect that all planets travel at the same speed. They can't possibly all travel at the same speed because some have farther distances to go than others. Carlos is correct. There is less gravitational force acting on planets farther from the sun. And yes, there is a slower speed for those farther planets from the sun, as we see in step 3. So looking at step 3 again, the farther you are out, the slower your speed is going to be. And that has to do with less gravity.